So we move in this chapter, chapter 9, on the center of gravity and centroids. There's a very similar concept for a lot of different terms. The center of gravity, the center of mass, the center of volume, the centroid, and the center of weight. These are all very, very similar concepts, especially if the density is constant and gravity is just uniform gravity. They tend to be the same term. So the first part, 9.1, is a great review of your favorite math class, calculus. And then we move into composite bodies, and there, instead of being a continuous system where we're using calculus and integration, we basically use summation. It's just very straightforward. And then hopefully today we'll be able to get through section 9.3. So what is the center of gravity or center of mass or centroid of a body? It's easy to think about weight. And so if I took a plank and I put some weight on it, maybe I put a crate here and a crate there and a crate there and a crate there and a bunch of different crates. And I said, look, I want to balance this by putting, a support either here or here or here or here or here. Which one would balance? With A, B, C, D, or E first? And clicker question, right? Where would I put that point, that pivot point, to support it? Under. You see what I'm trying to draw? It's like not all of them, just one of them. Which one would balance the system?
Are the boxes all equal in weight?
Yep, they all are equal weight. Yep.
Are they all the same distance apart?
Yeah, pretty much the same distance apart. Yep. As I've sketched it, it's a rough. So this was not a hard question, and I'm glad to see that everybody here is correct. Why was C the best answer? Because basically it balanced. And what's the concept here? In the presence of a gravitational field, you have the weight here down, the weight here down, weight here, the equal weights going down. And what's the key idea is you have this moment arm, moment arm, moment arm. All three of those want to rotate in the clockwise direction. This one has a larger moment, but they're balanced by this one's moment arm times the weight, that one as well as that one, and they're trying to make it rotate in the counterclockwise, and that's that balance point, isn't it? So weight is the easiest concept, even though we'll be talking about centroids of volumes and areas. So the centroid would be the center of the body, center of a line, area, or volume. We're going to emphasize continuous systems. So when you have a continuous system, you must set it up and solve by integration. We want to do that to reinforce the tools you took out of calculus. And when we get to a discrete system, that integration, that symbol for integration, its cousin is this symbol for summation. It took me a while in my undergrad education to see the similarities, recognize it. But that's what it is. They're both summation symbols. This one looks like the summation symbol. The integration does. But this is for continuous system. So the key idea is those moment arms. Sometimes it's hard to see in the equation, but if you have the center of gravity, you can think of what's the total weight of the system. That'd be the sum of all the incremental weights, and that turns into an integration for a continuous system. And then using that total weight times an average x distance is equal to the integral, or the sum over all of them, x dw's. So this would be like the simple equivalent system, the actual continuous system, and then that gives us the equation for x bar, 1 over the total weight, the integral of x dw, the actual location of every little chunk of weight that makes up the system. Similarly for the y and the z. You take that same, if you understand it for gravity, the same concept, and you do it for the center of mass. Take the g off. You have now the mass of the system is the sum over all the little chunks of mass. that same mass is used in the x bar equation. So x bar is 1 over m times the integral x dm. This product of x dm, that's a moment arm, a very little chunk of mass. And then you do the same for the center of area. So you take off density, took off gravity, take off density. Now you're down to just maybe an area or a volume, if you like to think of that, a volume. And then you can then do it also for a line. You can talk about the x bar, y bar location of a line in 2D. Here's an x and y problem, and maybe this is a line like this. You could talk about, oh, the center of gravity would be kind of here and for x bar and there for y bar. Well, let's solve a problem. Calculate the area and the centroidal location of that area. So this is that blue shaded area. It's plotted on the x and the y axis. And the x goes from 0 to 3, and the y goes from 0 up to 3 as well. But it's not linear, not the area underneath the straight line, but it's the area under the curve y is equal to x cubed divided by 9. Let's check it out. If I put x equal to 0 into this equation, does it return y of 0? Sure. If I put x of 3 into this equation, that would be 3 times 3 times 3. Does that return 3? Yeah, 27 divided by 9, that's 3. So this equation appears to be correct. So how do I calculate that area of the blue shaded? Well, I sum up all the little chunks of area. And you can start way back in Cal 2, you probably said, this is going to be my little chunk of area dx by dy, which is fine. And then you moved into strips. And so typically it would talk a lot about little strips of width dx. If I knew the height of that strip and I multiplied by dx, wouldn't that give me the little dA for that strip? Sure. So what is that dA? It's something times dx. In this problem, it's pretty easy. The height is a function of x. It's equal to y, or you replace it by x cubed divided by 9. Now I'm ready to integrate. We set it up in order of strips. So we integrate from the lowest x to the highest x. You integrate from 0 to 3. And that gives you the area. Can I ask you to do this integral on a piece of paper and then report it alpha or numeric response? Can I ask you to do that, please? So let's go ahead and do that. We pull out the 1/9, then we integrate x cubed. That's the beautiful integral you love to do. Isn't that 1/4 x to the 4 evaluated 0 to 3? And so now I have 1/9 times 1/4, and that, when I put in 3 to the 4th, basically I have 9 over 4. Well, it's 3 to the 4th minus 0 to the 4th, right? And then you pick up 9/4, which when you make the computation, what does that come in at? 2.25? Thumbs up if you agree. Let's go ahead and take a look. 2.25. All right. I'm going to do a lot of integration today. I'm not going to do every little bit of it. I'm going to set it up and then say, here's the answer. But you'll have to do it. Now, that gives us the area. That's done. Okay. In units of what? Did they put meters or centimeters or anything? They should have. Maybe we put meters and it's meters squared. But I think the units are left off. Now, what is a centroidal location? We're looking for x bar and y bar. The equation for x bar is 1 over area. We just calculated. The integral of x dA. All right, dA. And then likewise, 1 over area, the integral of y dA. Well, let's go ahead and how do I calculate the integral of x dA? Is that the integral of x times dA, which we found was x cubed divided by 9 dx? Do you see how we did that? Isn't this dA? Yeah. And then what about the integral of y dA? The integral of y dA. Okay, well, now I go back and I think about this strip. That strip had constant x, didn't it? That's why I just put in x times dA. But if I'm looking to calculate the centroid, I think about the y average of that strip. So what is y at, when I put in this integral y dA, what is y bar for that strip? What is y? It's half the height, isn't it? It's 1/2 the height. So what is the height? That's x cubed divided by 9. So basically it's the integral of 1/2 of 1/9 x cubed times dA, which is x cubed over 9 dx. All right? That makes sense? So we compute this integral. It's very similar to the area integral. We compute this integral. We take the ratios, and we're able to calculate our x bar to be 2.5 or 2.4, and our y bar is 6/7 or about 0.86, somewhere in there. Whenever you calculate these, maybe it's a good thing to try and draw them on your plot to see if they make sense. This is about 2.4 right in there. And this is about 0.89, right in there. Does that look like the centroid of that area? After you get a little better at it, maybe it looks reasonable. All right? Okay. Well, you would do the same thing here, calculate the area and then the centroidal location of this area. But this area is a little different. It's not where you're given a curve and then it's the area under the curve. It's actually the blue shaded is above a curve, isn't it? Well, do a little strip in dx. I often find it's easier to do a little strip in dx than in the other dy, but we can do it in dy as well, and maybe I will. But this is dx. And what is that height of that strip? That's the hard part. But it's not that hard, is it? Isn't it 2 minus, so 2, no matter where I'm at with respect to x, minus y, which is 2/9 x squared. Doesn't that give me the proper height? And so my little dA for that strip is equal to 2 minus 2/9 x squared times dx. That's probably the hardest part of this problem. All right, so now we'll do the integral. To get the area, we'll do the integral dA, right? Okay, then we say if I want x bar, I'm going to put 1 over that area, the integral x dA. So the hard part is to get the integral of x dA. Well, that's the integral of just add x. And then the dA we just had, 2 minus 2/9 x squared dx. And likewise for dy. Y bar, I mean. So y bar is equal to 1 over the same area integral of y dA. Here, for this y, I need to calculate the center of that strip. And so what is that y location of the center of that strip? So when I have the integral of y dA, I have the integral of, just average 2 heights. Average 2, and the bottom height, 2/9 x squared. That's the replacement for y. Do you see that in that strip? What is the centroid in the y of that little vertical strip? And then you multiply by dA, which was 2 minus 2/9 x squared dx. All right, this is a good review of Cal 2, is it not? All right, now, somebody says, I think it's easier if we do, instead of vertical strips, horizontal strips. You can do that too. You definitely can do that. So this would be a dy. All right, what is the area, the integral of dA, which is the integral of something dy? Well, what is this distance here? Instead of calling it height, what do I want to call that? It's the length of the strip. Well, the length of the strip is now with respect to the x-axis, so I have to change this equation around. Sometimes we can do it, sometimes we run into trouble. But wouldn't it be like y, 9 divided by 2 square root, and we'll take the positive for what x is? Yeah. Right? Just rearrange that equation, and now I know when I take the square root of something, it could be plus or minus, so I'm forcing it to take only the plus of that square root. And so this would be the integral of, the square root 9/2 y. It's kind of interesting, if you do this integral, and then you come over and do this integral, will you really get the same answer? Oh, the limits. I didn't emphasize the limits. With respect to the integral with respect to x, it's 2 minus 2 over 9x squared. What is my lower limit? It starts at 0. What is my upper limit with respect to x? It ends at 3. But they're not 0 and 3 for the y, are they? If I'm integrating with respect to y, it starts at 0. That's easy. But it ends at 2. So keep all those limits. 0, 3, 0, 3, etc. You can do the same thing to calculate the x bar and the y bar. You want to do the integral of x dA. If you use that vertical strip, I have to think about what is the centroidal x for that vertical strip. And that'll be the integral of 1/2 of the square root of 9/2. 9/2 times y, end of square root. That's the centroidal location of that strip, times the dA, which is 9/2 y square root dy. Integrate between 0 and 2. All right, well, here are the answers for this problem. The area is 4, x bar is 9/8 or 1.125, and y bar is 6/5 or 1.2. Okay. Some of you may be straight out of calculus. Maybe you always started with a little dx dy. That's fine. You just have to figure which do I integrate with respect to first. That'll give you the strip. And then what is the outer, the second integration? That'll sum up over all the strips. Well, not only do we do areas, we need to do volumes. So we have calculate the centroid of this homogeneous solid. That's typical. We don't have varying density. Homogeneous solid formed by revolving the shaded area. This is that shaded area right here. It's kind of gray. And we revolve that about the y-axis. Here's the x-axis, the y-axis, and the z-axis. It takes us a while to figure out what you get, but can you see when you revolve it, it's like a cone? But it's really not a perfect cone because of this profile. So in the x equal to 0, in the y-z plane, this curve that has an equation of z squared is equal to 1/16 y cubed. All right. Well, if we're asked to calculate the centroid of that solid, we're asked to calculate x bar, y bar, and z bar, right? One of those or more of those are equal to 0. So I'll ask a clicker question. For this solid, is x bar equal to 0? Yes, answer A, or no, answer B. So we'll change that to multiple choice. We can look at this object, we can exploit symmetry, and we can conclude possibly that one or more of those centroidal locations, x bar, y bar, z bar, is equal to 0. The first question is x bar equal to 0? when you revolve it, if I look in this line along that slope of that line, right? I try to move it over here. I move this slope. It's the same back as it is forward, isn't it? If I cut it in the YZ plane, if I just cut it at x equal to 0, if I cut it at y, does the front half and the back half look the same? Yeah, it's symmetrical, isn't it? It's symmetrical about that plane that goes through the x equal to 0 in the YZ plane. So the x bar is easy. The x bar is 0. I conclude that by my observation of symmetry. All right, let's do this one. Is y bar equal to 0? Yes, A, or B, no? That was a lot easier question, wasn't it? Because out here you have y bar, and you can tell it's probably out closer to 4. That's the location y is equal to 4 than 0, isn't it? And if you had to guess, I'd say, oh, it's beyond 2. I would say it's in the vicinity of 3 or maybe even higher. So no, it's y bar is not 0. Very good. Last one is z bar equal to 0, yes or no? Well, what does it mean, again, when x bar is equal to 0? That means that centroid is somewhere in the YZ plane. Okay, and we talked about cutting it in the YZ plane, and that goes to the centroid, 0, or through the origin, 0, and then being symmetric. Well, same thing here. Think about cutting in the XY plane, going through the origin, and then I look at the top half and the bottom half of that object, and is it symmetrical, a mirror image above and below? And it is. And so we conclude that yes, this z bar is 0 from symmetry. I was hoping to get a few more than 100, closer to 100%. All right. So right away it asks for 3 answers. 2 of them you give by observation according to symmetry. Now the next one we have to work with. It's a continuous system, so we're going to do some integration. And so what we want to first calculate, well, the equation to calculate y bar is 1 over the total volume times the integral of y dv. That's our basic equation. And to calculate the total volume, it's the integral of dv. So just do the first one, the simple integration, and then typically we tweak it or modify it to get the integral of y dv. Well, we want to integrate. Now, you can go back and you can do dx and dy and dz. Maybe that's the way your calculus, instructor taught and everything else. But then later, they go, look at, if I'm trying to sum up something like this, I know how to calculate the area of a disk. The volume of a small disk, right? So if that disk has a uniform radius, r, and it has a little thin thickness, dy, what is the little volume of that disk? Isn't it pi r squared dy? All right, and what exactly was r? That's like the height, or in this case, it would be the z. So it's equal to pi z squared dy. Oh, and just this is the way some of these problems work. Is z squared easy to put into the? Sure, we can replace that z squared by 1/16 y cubed dy. Now that's what the dv is that we want. And now we turn a volume integral into a one-dimensional integral. We're summing over all these little disk volumes to calculate the total volume. And so this would be the integral with respect to y of pi over 16 y cubed. And what is the lower limit? We'll start at 0 for y is 0, and we'll end at y equal to 4. And so at this point, you can perform the integration. The volume is 4 pi or numerically at 12.57. Here they do give units of meter. It's a meter to the cube. All right. But we want to get y bar, so I have to compute this integral. So instead of, I'm going to just go back. So we 1 over, let me do this. 1 over 4 pi, that's our total volume. The integral of y, because we're integrating with respect to y, that just plugs in. And then what did we have for dv? Pi over 16 y cubed dy. And it goes from the same lower limit, 0, to the same upper limit, 4. And when we make that computation, the y bar comes in at 16/5 meter, or y bar is equal to 3.2 meter.